Hi everybody and welcome to a new exciting video in the audio signal processing for machine learning series. Last time we looked at the theory behind the discrete Fourier transform and the fast Fourier transform, which is a flavor of discrete Fourier transform. This time I want to actually extract the Fourier transform coefficients using Python and specifically NumPy. Beyond that, I'm going to show you also a bunch of different magnitude spectra for instruments which play the same notes so that we can at least have a glance into why we perceive their timbre differently. Okay, so let's get started with our Jupyter notebook. And here, first thing, I want to import a few libraries that are going to be useful for our purpose today. So I'll import NumPy as NP, and as I said, we'll use NumPy to extract the fast Fourier transform. Then I'll import matplotlib.pyplot as PLT. We'll use this library to plot the magnitude spectrums, and then I'll import OS. I'll import Librosa to load the audio files, and finally I want to import ipython.display as IPD, and we'll use this to listen to the audio files directly in our Jupyter notebook. Okay, so now what I want to do is just like load the audio files and show them and listen to them directly here in the Jupyter notebook. And so first thing that I want to do is create a base dir, and that is going to point to the directory that contains all the different audio files that I want to show you guys. And so I'll start with home, and then Valerio, then PyCharm projects, audio signal processing for ML, and we are at the 14th. And finally, I'm going to have this audio directory here. Okay, so this is the base there, and then I'm going to have this, let's call it Violin file, and so you'll see it here. Where is it? Should be over here, right? Okay, so here I'm in the base here, and as you can see, we have a bunch of different files. So let me just go back to the Jupyter notebook. So the Violin file is called violin.c.wav. Then we have the sax file, and this is called, if I remember correctly, sax.wav. And then we have this piano file, which is equal to piano.wav. And finally, we have the noise file. So we're also going to see the magnitude spectrum for some noise, and this is called noise.wav. Okay, but the piano one is called piano.c.wav. Okay, good. So now let's try to load this audio directly into Jupyter Notebook so that we can listen to that. And so for doing this, we'll do an ipd.audio, and we need to pass the file path to like all of these different files. And so we'll do a os.path.join, and we'll pass the base here as well as for the violin file over here. And yes, as you can see, we loaded that. I'm going to load all of these guys first, and then we're going to quickly listen to them, but they're very, very short. Okay, so yeah, let me do this sax file. So I'm gonna pass in the, where is it? The piano file. And finally, I want to pass in the noise file over here. Okay, so yeah, let's listen to this first thing. So here is a C4 notes for the violin. Okay, so the C4 notes, so think of like the piano keyboard. The C4 is the middle C, so it's the C at the center of the keyboard. Then we have a C4 note for the saxophone. Okay, and then a C5 note for piano. So this is still a C, but it's an octave above than like the middle C. And finally, we have some noise. Yeah, we're all used to this kind of noise. Next, we want to load these files as NumPy arrays. And for doing that, we are going to be using LibRosa. Okay, so I'll load the violin C4 sound, and I'm going to get back also the sample rate. And I'm going to use a LibRosa dot load, and what I want to pass in is this guy. So basically the file path to the violin file. Okay, so this is for violin, but we should do the very same thing for sax, and sax is going to be sax C4. Now the sample rate is going to be defaulted to 22,050 hertz, and we just need like the first one. Then I mean, like here the sample rate is going to be the same, so I'm just going to be using an underscore because I say, well, I really don't care about that variable. Okay, so this is the same, but here it's not the violin file, it's actually the sax file. Then we have the piano, but it's not C4, it's going to be C5. Once again, I'll put an underscore here, and this is going to be a piano file. And finally, here we have our noise, and let's pass in the noise file. So yeah, so now we should have all of these guys with us. So let me show you that the sample rate is 22,050 hertz, and you can see it here, and that's the default value for LibRosa, so that's fine. Now let's take a look at the violin C4. So this is a NumPy array now. So, and this is basically like the waveform associated with this audio file. And if we take a look at the shape, we're going to see that this is like an array, and which has like only like one dimension, and in that one axis we have around 60,000 samples, and this is the number of samples that we have like in the audio file, which is cool. Okay, so now let's try to extract the Fourier transform coefficients, and I'll call this for, let's say, the violin sound. So we'll do a FT, or let's do violin FT, where FT stands for Fourier Transform. And so for doing that, we'll use a numpy.fft.fft. Now, if you feel that this fft.fft is redundant, I'll tell you that this first FFT is a module that contains a bunch of different implementations of the fast Fourier transform, one of which is the classical FFT. So that's why you have like this double FFT thing here. Okay, so here we need to pass the actual signal, right? So this violin C4. And now basically by doing so, we move from the time domain here to the frequency domain over there. Okay, so now let's take a look at this Fourier coefficients. So let's take a look at the shape of this array, and we'll take it over here, and we'll do a violin ft dot shape. And as you can see here, so this is this has the same shape that we had for the signal itself. Now, if you don't remember why that's the case, I really suggest you to go check out my previous video, which should be here, on the theory behind the discrete Fourier transform. But basically, the idea in a nutshell is that we're gonna have like as many frequency bins as the number of samples that we have in the original time domain representation. So this checks out. Okay, so now let's take a look at what we have for one frequency bin. So we're going to take like the first Fourier transform coefficient, Fourier coefficient for Violin FT. And as you can see here, this is a complex number. And you have the real parts here, and here you have the imaginary part of this complex number. Now, once again, if you don't know what I'm talking about like complex numbers, I suggest you like to go check out my video on complex numbers, and it should be over here. And then, if you can't remember why the Fourier transform like produces complex numbers, I suggest you to go check out this video that provides you with a lot of information about the Fourier transform itself. Okay, so here we have like this complex number, and we know that this complex number provides information both about phase as well as the magnitude. And now the thing is that for most applications in AI audio, we usually don't care that much about phase. So when we analyze signals, what we really care is to understand how much each frequency is present in an audio signal, and for that we just need the magnitude. So what we do usually is we discard the information about phase, and we only retain information about the magnitude. And so we move from the Fourier coefficients to the magnitude spectrum. So how do we do that? Well, that is very simple, because we just like take the absolute value of the Fourier coefficients. In other words, we can take the magnitude spectrum of the violin sound here by taking numpy.abs, which stands for absolute value of the violin FT. So we pass the Fourier transform coefficients to the absolute value function, and we get back the magnitude spectrum. Now, this is not the violin, it's just violin like this. Oh, no, sorry, I just messed up everything. So it's not the violin, but it's the violin. Okay, so now let's take a look at what happens here if we visualize like the first a coefficient for the magnitude spectrum. Now, as you can see here, we don't have the a complex number anymore. We actually have one single like real number, and that is indeed the magnitude associated with this initial frequency bin over here. Okay, so now you should have an idea of how to extract the Fourier transform and how to calculate the magnitude spectrum. But what we want to do here next is to actually visualize the magnitude spectra for all of these different sounds that we have here, so that we can compare them. Okay, so for that, I'm going to create a little function called plot magnitude spectrum. So this function is going to accept a few parameters. So first of all, the signal itself in the time domain. Then it's going to take a title, so that we can give a title to our plots, and then it's going to accept a sample rate. Okay, yeah, why did I do that? Well, okay. So now the first thing that we want to do is to calculate the Fourier transform, and we already saw how to do that, and we'll do a numpy.fft.fft, and we'll pass the signal. Then we'll calculate the magnitude spectrum, and for that we need to create like this np.abs, and we'll pass the Fourier transform. And then we want to plot the magnitude spectrum. And so how do we do that? Well, first of all, we need to initialize a figure. And so we'll do a plot.figure, and we'll pass in a fig size. And this is a keyword argument. And here I'm going to pass in 18 for the width and 5 for the height. And then the next thing that we want to do is to kind of like create the x-axis, and these are going to be like our frequency bins. And so we can call this like frequency. And so how are we going to do this? So we're going to be using this lin space a function from NumPy. So let me just like write this, and then I'll explain what it does. So we'll take this between 0 and the sample rate, and then here I'm going to pass in the length of magnitude spectrum. So what I've done here is basically taking a range. So we're going to have like the frequency, which is between 0 and the sample rate. And then what I'm going to do is I'm going to like create as many divisions, as many frequency bins as the length of the magnitude spectrum. So this is for frequency. Then what we'll do next is just like plotting. So we'll do a plot. We need to pass the x-axis, and this is going to be frequency. Our y-axis is obviously the magnitude spectrum over here. And then what we want to do next is to pass the x label. And here as the label for our x-axis, we'll put in frequency, which is measured in hertz. And then we'll do a plot.title, and the title is going to be equal to title. And finally, we'll do a plot.show so that we can show our plots. Okay, so now if I haven't made any mistakes, we should be able to visualize the magnitude spectrum here. So now let me pass the, let's take the Violin C4 over here. I'll pass that signal, then as the title, I'll just pass in Violin, and then the sample rate is going to be equal to sample rate. Let's see. Oh, here we go. Nice. So we have our magnitude spectrum, and as expected on the x-axis, we have the frequency, all the different frequency bins expressed in hertz. On the y-axis, we have the magnitude. Now, if you remember from my previous video, you probably know that like what we're going to get out of like this spectrum is some kind of like central symmetry. And indeed, you see that we have like central symmetry. So basically, we can kind of like consider only the frequencies up to like the center point, which is the Nyquist frequency. Okay, so let's do that. And so I want to like make this like a little bit more flexible. So what I'll do is I'll change this function, and I'll introduce like another argument called a frequency ratio. And I'll put like this as default equal to 1. Okay, but basically here I want to calculate the number of frequency bins, right, using the frequency ratio. Now, this is going to be equal to the frequency that we have, well, the length of the frequency that we have here, and then we'll multiply that by the frequency ratio. And obviously, like this number is going to be a float, so we need to cast it to an integer. So I'll do this like that. Okay, and so now, like by doing so, we can take like only a part of the original number of like frequency bins. And so now what we can do is just like go in here and slice the frequency and magnitude spectrum variables here, arrays, and only like consider from 0 up to the number of frequency bins that we want to consider. And I'll do the very same thing for the magnitude spectrum here. Okay, so now if I put the frequency ratio equal to 1, well, we still have the same thing. And as you can see, the frequency in hertz goes up to 22,050 hertz. Yeah, let me just like remove this. Oh, by the way, given, yeah, I saw this. So this is the Sound of AI Slack community. And so if you want to join, here you can get like information about like all things like AI audio and AI music, and you can also like network with very, very cool people, know things about like the like community like updates and new things. You can ask for advice, or you can just talk about papers and other cool stuff all around like AI audio. So if you're interested in joining the Sound of AI community, I'll leave you the sign up link in the in the description below. After this little teaser with the Sound of AI Slack community, let's go back to like the plot here. And as we said, so when we have the frequency ratio which is equal to 1, still we get all of our the frequency like has all the original frequency bins, and so it's up to the sample rate frequency, which is 22,050 hertz. But if we change this, say to 0.5, we'll just have we'll just consider the frequencies up to the Nyquist frequency, which is half the sample rate, which in this case is 11,000 hertz. And but still here we see that most of the energy is contained in like lower frequencies. So to zoom in, I'll just like put a 0.1 here, and as you can see here, like this is like nice because here we can actually see the different frequencies that are like involved in shaping this violin C4 sound. And so here at around 2060 hertz, we have a first peak, and this is the fundamental frequency of C4. And indeed, like this is the frequency of a C4 note. Then we have like the first harmonic, which should be around 520 hertz, which is very present. And then we have the third, the fourth, fifth harmonic, and so forth. The interesting thing here is that the first harmonic of this violin C4 sound has more energy than the fundamental, so which is kind of like interesting in itself. Okay, so now let's compare this with the saxophone sound. So sax C4, and here I'll pass in sax, and as you can see, we have a quite similar spectrum, magnitude spectrum here, and this is to be expected because like both instruments are playing the very same note, which is this C4, and so you see I pick here on around like the fundamental frequency and on the first harmonic, but on a closer look you'll see that the relative presence of these harmonics and the fundamental is different for the violin and the saxophone. And so this is one of the reasons why we perceive these sounds as different in timbre. So they still have like the same frequency because they're both playing the same C4 note, but they sound different. And one of the reasons why that's the case, it's because their energy content, which we can see through this power spectrum, is different. Okay, so now let's take a look at the C5 note on the piano. So I'll do a piano C5 and let's call this piano. Right, and now obviously like the fundamental here is not 260, but it's rather 520 hertz because we are an octave above C4 because we are in C5, and that basically doubles the frequency of the fundamental. But the cool thing here is that you can see that the peak is on the fundamental. Then the first harmonic partial is kind of like less present than the fundamental, and then like the other like harmonics just like fade away in their presence. This is different from what happens with the violin and the saxophone, where the first harmonic partial is more present than the fundamental. Okay, so now as a final thing, let's take a look at the noise signal. So we'll have like noise here, and I'll put in here noise. All right, and as you can see here, what happens is that you have a lot of activity, a lot of energy in all the different frequency bins. For sure, we have some kind of like peak here towards like the lower frequencies, but then as you can see, like all the frequency bins have a little bit like of energy in them, and that's what a noisy signal looks like. Okay. Cool. So I think like we did like some cool stuff like in this video, because now you should be able like to extract the Fourier transform with Python using NumPy, and then you should also be able to visualize the magnitude spectrum using matplotlib. And finally, we also now know the difference between like different instruments and what that like means in terms of like perceptual characteristics like of sound. Okay, so now one thing that I want to draw your attention to before I dash off and I finish off like this video is that each of this like magnitude spectra is a kind of like a snapshot that we take, and it's a snapshot that provides us information across all the duration of a sound. It doesn't give us any information about what happens with relation like to the frequency, like second by second or like moment by moment. We just lose that information because we average everything across all the duration of a sound. Wouldn't it be fantastic if we could have information about the frequency and it as a function of time as well? Well, that would be fantastic indeed, and it's going to be the topic of my next video, which is going to introduce the theory behind the short-time Fourier transform. And the short-time Fourier transform is going to enable us to extract the spectrum from an audio signal, and this is the main currency that we use in AI audio and music information retrieval to make sense of digital audio signals. So stay tuned for that. That's all for today. I hope you've enjoyed the video. If that's the case, please leave a like. And if you haven't subscribed to the channel, please consider doing so. If you have any questions, as usual, feel free to leave them in the comment section below. See you next time. Cheers.